Cosmic fires, the birthplaces of black holes. Imagine a star, much more massive than our sun, reaching the end of its life. It has burned through all its fuel, fusing hydrogen into helium and then into heavier elements. The outward pressure from nuclear fusion can no longer resist the relentless inward pull of gravity. The core collapses, leading to a supernova, an explosion that can outshine an entire galaxy. Gravity crushes the star's remains into a singularity. This point is a place of infinite density and zero volume, a cosmic abyss from which nothing, not even light, can escape. Event horizon, the point of no return. Imagine approaching a black hole, drawn in by its irresistible gravitational pull. The black hole itself isn't visible, shrouded in darkness, but the space around it appears distorted, like a funhouse mirror. This distortion is caused by the black hole's immense gravity, warping the fabric of space-time itself. At a certain distance from the black hole, you would cross an invisible boundary known as the event horizon. This is the point of no return, a cosmic Rubicon that once crossed seals your fate. Beyond this boundary, the pull of gravity is so strong that nothing, not even light, can escape its clutches. You wouldn't feel anything special as you crossed it, but your destiny would be inexorably linked to the black hole. No matter how powerful your engines, no amount of energy could propel you back across the event horizon. You would be trapped, destined to journey toward the singularity at the heart of the black hole. Singularity, where physics takes a back seat. At the very heart of a black hole lies the singularity, a point of infinite density and zero volume. It is here that our current understanding of physics collapses, unable to describe the conditions that prevail. The singularity is a place where gravity runs amok, crushing all matter and energy into an infinitesimally small point. Imagine all the mass of a star, or even 1,000 stars, compressed into a region smaller than an atom. That is the singularity, a place where the very fabric of space-time is torn apart. The laws of physics as we know them simply cannot cope with the extreme conditions at the singularity. Some theories suggest that the singularity might not be a point at all, but rather a ring or a more complex structure. Without a complete theory of quantum gravity, the true nature of the singularity remains one of the greatest mysteries in modern physics. Spaghettification, a not-so-pleasant end. Let's imagine, for a moment, the unfortunate experience of falling into a black hole. As you cross the event horizon, you wouldn't feel anything special at first. However, as you venture deeper, the immense gravitational forces would begin to take hold, stretching your body like a piece of spaghetti. This process, known as spaghettification, is a consequence of the tidal forces exerted by the black hole's gravity. These forces are stronger on your feet than on your head, stretching you out in a process formally known as tidal elongation. As you fell deeper into the black hole, the difference in gravitational pull between your head and feet would become more extreme, eventually ripping you apart. Your elongated body would continue to be stretched and torn apart, atom by atom, until you were reduced to a stream of subatomic particles spiraling into the singularity. Section 5. Time warp. A black hole's time-bending power. One of the most mind-bending aspects of black holes is their effect on time. According to Einstein's theory of general relativity, gravity warps time, causing it to slow down in stronger gravitational fields. This means that time runs slower near a black hole than it does farther away. Imagine you could observe a clock falling into a black hole. As the clock approached the event horizon, you would see it tick slower and slower. From your perspective, the clock would appear to freeze at the event horizon, never quite crossing over. However, from the perspective of the clock itself, time would continue to flow normally. This time dilation effect has profound implications for our understanding of the universe. Section 6. Hawking radiation. Black holes aren't so black after all. Black holes, despite their name, aren't entirely black. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery showing that black holes can actually emit radiation. This radiation, known as Hawking radiation, arises from quantum effects near the event horizon. According to quantum mechanics, empty space is not truly empty, but rather teeming with virtual particles that constantly pop in and out of existence. Near the event horizon of a black hole, one particle of a virtual pair might fall into the black hole, while the other escapes into space. This escaped particle carries away some of the black hole's energy, causing it to slowly lose mass over time. Hawking radiation is incredibly faint, far too weak to detect with current technology. Section 7. Black hole evaporation, the slow fade of a cosmic giant. Hawking radiation, while faint, has a profound consequence for the fate of black holes. As black holes emit Hawking radiation, they slowly lose mass and energy. This process is incredibly slow, taking vastly longer than the current age of the universe for a typical black hole to evaporate completely. However, as a black hole loses mass, its Hawking radiation intensifies and the evaporation process accelerates. Eventually, the black hole will shrink to a minuscule size, and its final moments will be marked by a burst of high-energy radiation. The timescale for black hole evaporation is mind-bogglingly long. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate. Section 8. Supermassive black holes, the heart of darkness in galaxies. While stellar mass black holes formed from the collapse of massive stars are fascinating, the universe harbors even more extreme objects, supermassive black holes. These cosmic titans, millions or billions of times more massive than our Sun, lurk at the centers of most galaxies. The origin of supermassive black holes remains an active area of research, but they grow by accreting matter from their surroundings and through mergers with other black holes. Supermassive black holes play a crucial role in the evolution of galaxies. Their immense gravitational pull influences the orbits of stars and gas, shaping the structure of their host galaxies. Section 9. Peering into the abyss, unraveling the mysteries of black holes. Black holes, once considered mere theoretical curiosities, have emerged as fundamental constituents of the cosmos, shaping the evolution of galaxies and challenging our understanding of the universe. From the event horizon, the point of no return, to the singularity where physics breaks down, black holes continue to captivate our imagination and inspire awe. While we have made significant strides in understanding these enigmatic objects, many mysteries remain. What happens to information that falls into a black hole? What is the true nature of the singularity? How do supermassive black holes form and evolve? The quest to unravel the secrets of black holes is a journey into the unknown, pushing the boundaries of our knowledge and technology. As we continue to explore the cosmos, black holes will undoubtedly continue to challenge and inspire us, beckoning us to delve deeper into the mysteries of the universe.